Hi, it's John Williams here at MIT, and I want to talk today about hash functions and how they're used in blockchain. So as you learn more about blockchain, you're going to see a lot of use of these hash functions. So a hash function can take the letters or numbers in a document, and by passing those through the function, we get a kind of fingerprint. We get a number of a fixed length out from the hash function. So typically this will be 160 bits long or 256 bits long. The interesting property, and here's an example, we've got hello and we use the numeric values corresponding to each letter. So H is 8, E is 5, etc. And here we just add them up and we get 52. And if we changed any of those letters, obviously the total would probably change and we might have a number like 73 or something like that. Now, the hash function is a little bit more complicated than that. It has some interesting properties. So here you could see one of the properties would be that from the number 52, from the hash function, we can't really know that it was hello that created that. Some other combination of letters could add up to 52. This is called a one-way function. So from hello, that will always give us 52. But from 52, we don't know what caused the hash to be 52. Okay, so let's take a look now at a little demonstration of a hash. So here we'll put in a space and you'll see that that has a hash ending in 9C6. Let me put THE. You see the hash is changing quite radically. So an interesting property is that sometimes we get a 0, or we might get 2 zeros. In proof of work that's used in blockchain, we have to find hashes that start with leading zeros, and we do it by adding numbers in. So here I happen to put the letter Q, but if, for example, I put a 1, no, that doesn't give me another 1, no. I'm going to keep adding ones. At some stage, we're going to get a leading 0. So by adding a number to the document, we might be able to create a hash with it there. Now I've got a leading 0. You see how many ones I needed to add. Now you can imagine that if I want to try and get 2 leading zeros, I might have to search quite a large space to get 2 leading zeros. So let's go back to our slides and see how this is used in blockchains. Typically, we have transactions or documents in a blockchain. We want to lock them. Now, instead of just locking them one by one, what we can do is we get the hash of each document. So document 1 is a hash. There's 0, 1, 2. Now we combine these hash 0 and hash 1 together. So I've got a number, say 160-bit number, and another 160-bit number. And I pretend that that's in a document. And now I can create a hash of those 2 hashes. And so on until we get a top-level hash. Now, if any of the documents down below here change, this top-level hash will change. This is called a Merkle root, and this is called a Merkle tree. And we use these Merkle trees in blockchains. So let's see how we use them. So here now is our Merkle tree. You see it here of transactions. So this is Bob sends Alice 2 ethers or 2 bitcoins, whatever. We take a number of transactions, we create this Merkle tree, and we take the Merkle root and combine it with the hash of the previous block. To mine a block in, say, Bitcoin, you need to take the previous hash. The Merkle root is also a timestamp and some other signatures, but you need to add a thing called a nonce. And a nonce is just a random number. We're going to change this nonce until we get a hash with leading zeros, with 5 or 6 leading zeros. Okay? And so what locks this block into place is solving this puzzle, so we get the leading zeros, and the fact that we've used the previous hash locks block 11 onto block 10. And then we take this hash, and that'll be put into block 12, and another load of transactions will be put in. So this is the way that the blockchain is created. The transactions must be stored separately. If we want to look at them, they need to be stored elsewhere. but what goes into the blockchain is the Merkle root of all those transactions in that block. So that's the way transactions are stored. Okay, we'll go into more depth about exactly the blockchain in the next talk.